Good day for everyone. My name is Wilendran Al-Himarimutu. My metric number is 241111015. So today I would like to explain about Reynolds transport theorem. Okay, introduction to Reynolds transport theorem. What is Reynolds transport theorem? A theorem that bridges system Lagrangian and control volume Eulerian perspective in fluid mechanics, and it used to analyze conservation of mass, momentum and energy. For example, we will take these two deodorant spray can. The A1, we will focus at the boundary inside of the can and the sprayed mass or sprayed gas. For B, we will only focus inside of the spray can. So this concept, as I mentioned previous, this will include Lagrangian and Eulerian. For the A, we follow the fluid as it moves and deforms. This is the system approach. For meanwhile B, we consider a fixed interior volume of the can. This is the control volume. If we add system approach and control volume, we will get the Reynolds transport theorem. As example from this slide, we have a system of pipe flow, and we have inflow and outflow, V1 and V2. So this is equation. This equation applies at any instant in time where it is assumed that the system and the control volume occupy the same space at the particular instant in time. So as we mentioned Lagrangian and Eulerian, if we combine both of them, we will try to figure out the inside volume or inside property. Now let B represent any extensive property such as mass, energy or moment, and B over M represent the corresponding intensive property, and T plus delta T will be expressed as this equation. So subtracting the first equation from the second one and dividing by delta T will give you this equation, and we must make the delta T into 0. We get all the same values and we will get this equation or this, and so on. As it's mentioned here, if theta less than 90 degrees, it will be outflow. If theta bigger than 90 degrees, it will be inflow. Meanwhile, if theta equals with 90 degree, there will be no flow acting on the surface. Outflow and inflow of mass across the differential area of a control surface have two different examples. One RTT fixed CV, another one alternate RTT fixed CV. Here we have three equations for relative velocity, RTT non-fixed CV, and steady flow. So here are the equations for Reynolds transport theorem applied to a control volume moving at constant velocity. As example here, we can take a car that pushed by a water jet. So here are the control volume of the car, and for find the control volume, we can make VR equals to V jet minus velocity of the jet minus with velocity of the car. An example control volume in which there is one well-defined inlet 1. Here are the inlet 1 and two well-defined outlets, outlet 2 and 3. In such cases, the control surface integral in RTT can be more conveniently written in terms of the average values of fluid properties crossing each inlet and outlet. So we have the approximate RTT for well-defined inlet and outlets. The equations are here, and we can use these equations for find more the solution for Reynolds transport theorem.